Devrat, mute Professor, unmute Professor Kanemitsu,
Yes, sir.
and then mute yourself also. So a very good morning to everyone joining us today in the fourth and the last lecture of our ongoing uh, popular mathematics lecture series. We, we have today, first of all, I would like to welcome you all on the behalf of Bahu Banarsidas University. And today, our speaker is Professor Shigeru Kanemitsu from, he's a visiting professor at Kyushu Institute of Technology, Japan. Uh, Professor, he's one of the very senior mathematician. Uh, Professor Kanemitsu has an experience of more than 37 years working at Kyushu University and Kinki University in Japan for almost 37 years in various capacity. He has been the chairman of Division of Electrical and Information Science of Graduate School of Advanced Technology of Kinki University, and has held many prestigious positions over the period of during last 37 years. And he has been the visiting professors at very prominent places in different countries, such as he was the visiting professors at Tata Institute of Fundamental Research, Mumbai, Institute of Mathematical Sciences, Chennai, uh, and University of Rome, Italy, University of Victoria, Canada, and Witwatersrand University, South Africa, and many more university. It's not possible for me to list all the university. He is an specialist uh, of number theory, spatial functions, zeta functions, L functions, and model form. And he has made some very significant contributions in these areas of mathematics. And he has published 135 research papers, has collaborated with the mathematicians across the world. He has also published 32 books on various topics in number theory, complex analysis, zeta function, spatial functions. And his latest publication is from complex analysis to meta science, a stroll around the boundary and beyond behavior, similarity, and duality, which is coming up from the word science. So it's my pleasure to have Professor Kanemitsu with us as a speaker this morning in the last session of Popular Mathematics Lecture Series. I extend a very warm welcome to Professor Kanemitsu, and I'm really thankful to you for accepting this invitation to speak in this series. And I'm sure that uh, the participant will enjoy. They will be exposed to many ideas, and it is going to be a very successful session. So I'll at the end I'll request all the participants, if you have any question to ask from Professor Kanemitsu, I'm sure he will be happy to answer your questions. But please, we have put everyone in mute mode to avoid any disturbance in this session. So if you have any question, you can simply type it in chat, and at the end of the session, it will be answered by Professor Kanemitsu. So I once again welcome you all to this last session of Popular Mathematics Lecture Series, and thank you for joining. And over to Professor Kanemitsu.
Now, can I share the screen, right?
Yeah. Sure, you can.
Okay.
You can.
Oops. It doesn't work yet. No. You are hindering sharing.
I'll check once.
Yeah.
Yeah, we have changed the status. You can. You can now.
Oh, yes. Then this one, I think.
Yes.
Is this big enough? No.
Yeah.
Probably no. Is this big enough?
No,
No.
I'll. It will be better if you open it in PDF, not in the browser, as we did yesterday.
Oh, no, not this one. Sorry. The other one. Not this, but this one. Huh?
You can close and restart.
This one, right?
Yeah. You can make it full screen. Control N.
Yes. Full screen mode.
Yeah.
Oh, does it work?
Yeah. Yes.
Can you see?
Yeah, it works.
Okay, so good morning in India. Good afternoon here in Japan. We have a 3.5 hours time difference. Today my talk is not mathematics, but something which may be useful in your career from now on. And the title is a little bit strange. Looks like math aesthetics, mathematics. So I'm very thankful to Professor Ahmad Ali.
Professor Kanemitsu, we cannot see you.
Why?
Is your cam on? Yeah, I can see you.
Oh.
Yeah.
Can you?
Yeah, I can see you. You can go ahead.
Okay. So I'd like to thank Professor Ahmad Ali for giving me this chance. This is very exciting for me. I met him, I remember meeting him in 2001 here in Lucknow, when all of us were younger, by 19 years, I think. And I would like to thank Professor J. Mehta for helping me to prepare some materials for this talk. In the beginning, I was planning to give a more mathematical talk, but Professor Ahmad Ali suggested that it should be more accessible to everyone. So today, I'll give you this one, I powers dominations. Actually, domination is an anagram of admonitions, I powers. So that I can give you some hints, very practical advices so that you can realize your dreams. And mainly we use the notion of association, which is not only mathematics, but this is general to and intrinsic to human beings. You may find this talk very rambling, but see, our way of thinking is very rambling itself. So the general feeling is that the mathematics is a set of hard computations and not relevant to you. But this is true in one sense, but most here, I'd like to debunk this wrong idea that mathematics can give you everything, deeper perspective of everything. And so mathematics is the ABC of all thoughts. You don't say, I'm DEF. So it's a way of thinking, because it gives meta science, and meta science gives a bird's eye view of everything. So here, today you learn association, omission, and Cartesian product. These are three topics. Association is here's the one association. Something is here. I want to remove this, but anyway. I'll show you some examples. One, Atbash, here you see, we are living in the world of Babel. And Babel associates, it is associated with Atbash cipher, which will appear later. And then you are associated with ciphers and codes, because these are the two sides of one coin. Then you may be associated with Dan Brown's Da Vinci Code, and you are associated with Da Vinci. And I tell you 7 principles Da Vinci, and there in Dan Brown's Da Vinci Code, we find Fibonacci numbers. And with them associated a golden ratio, which is the topic of Michel in the first talk. So you may know about Caesar's cipher, right? With Caesar, you may be associated with the names of months. Which month of, I think we are now in July, right? And after July, you should have September, October, November, December. And these are Romans, hepta, octa, nona, deca. So why September is not July? It's very simple, because July is the name of Caesar, Augustus. Next month will be August. And we'll see 2 associations, Caesar's cipher and Caesar's last breath. So omission is, by omission, ignoring things, unnecessary things, irrelevant things. Mathematics is very good at this. In mathematical terms, this is called equivalence relation. So by this omission, we can group together very similar things, like coffee cup and the donut. For topologists, they are the same. One of the closest relation between math and art is symmetry. And symmetry, the symmetry itself has a meaning that the sim means similar, right? Metry means measure, right? Meter. And meter comes from a very old Sanskrit, amita. Amita means non-measurable. So I want to show that mathematics is a science of classification. Not only, but one of main purposes to classify things. And numbers measure size, and groups measure symmetry. So see the cipher is this. Suppose we have 26, nowadays we have 26 alphabets, right? So we just label them by 0 to 25, and then see the cipher is simply, C means ciphertext and P is plain text. C equal to P plus 3 modulo 26. Modulo means that you just ignore difference by 26. If you get 28, then it should be 2, meaning B. This is the cipher. And we are trapped by the gravity. Nothing can escape from the gravity of the Earth. So we may be breathing in our breath, see the particle in Caesar's last breath. So everything is circulating. So if we do harm to our environment, it will eventually do harm to us. First, I'll tell you about the environment in which we are living. And before that, I tell you another thing, coordinate ciphers. The polybial cipher is like arranging 25, because I was not there in the old alphabets, only 25. So you can just arrange in square, right? And then F this is wrong, 1, 2, 6, anyway. So very curiously, in Japan, we have 49 alphabets. This cannot be just coincidental, because 7 times 7, right? Square, 7 square. So there are associations with Descartes. You see this year, 1619, when no one was born, right? When Descartes was 23 years, he imagined the world now. Now we are living virtual world, and everything will be dealt with rationality by mathematical computation. So this is one thing. Another is this, that in this book, White Gloves, they also mention great calculation theorem, meaning apparently the notion, the notice by Descartes. Descartes, one of the most important saying is cogito ergo sum. This means I think, therefore I am. This is three associations with Descartes. But the mathematically most important thing is Cartesian product. This is just coordinates. But to express one point, a point in space by three coordinates is a remarkable thing. So we just go on. I'll show you one example of a Cartesian product in molecular biology in this book by Gromov and Carbon, Mathematical Slashes of Molecular Biology. You can see the situation of homeostasis. It starts like this, becomes in a very active place, there is an attractor, and then replication occurs, and then replication appears as a multiplicity of nearly identical cells represented by the Cartesian product of many copies. So here we see the practical application. So here we come, we come to Atlas cipher. We are living in the world of and I'll show you. You just arrange the alphabets in this way, A, B, G, right? And then in the opposite direction. So if you read this, then At Bash. So this is called At Bash cipher. And if you recipher this, sh means BB, right? K is L, B Bill. So if you supplement vowels, you get Babel. Babel means Babel Tower, Tower of Babel, where all science. If you are a major, if you're majoring in different sciences, you can never talk to each other. This is quite wrong. This is a sectionalism of 20th century. In the new century where we are living, it should be like Newtonian, neo-Newtonian era, where we can communicate each other in different disciplines. So let me read this. No problem can be solved from the same level of consciousness that created. This is words of Einstein. We must look at things from a higher point of view. So here I'll give you preaches. This means admonitions. Now, first I will tell you square hypothesis, 5 to the 2, 25. Most of you are below this. And then 36. During this period, you have to establish yourself, right? 49 this is the middle age when you have to complete your career. 64 is a retirement age. 89 is already average life. But suppose you live long. I'm going to live 120 because I cannot survive up to 121. 121, apoptosis starts and our cells will be gone. This is an analect of Confucius, more or less the same. Confucius decided to choose learning at the age of 16, for instance, right? 16 and then what was 16, 25, right? And 40, then 49. So somehow corresponded, right? 60, it's time when mind of tranquility. Age 70, Because at that time in old China, ancient China, this was a very, very long age. So if you replace truth by your profession, then this applies. So here, this is the most important point. 7 principles of Leonardo da Vinci. The first is curiosity. If you are measuring something very special, you may not be interested in other things. This is not the right attitude. Then you should learn from mistakes. And you have to refine your senses and enliven your experience. This is very important. And this is what I want to stress. You should be willing to accept ambiguity, paradox, uncertainty, sometimes imperfection. Because in mathematics, we look for perfection, and sometimes we fail. But if we allow a little bit, deviation, then it's something gives much more better wider perspective. This is left, right brain thinking. Some time ago, this was very famous. And you have to have a strong body. If you want to make a good research, you must have a strong body. System, also this is very common in modern thought. So item 4 is important, imperfection. You allow imperfection. And these items are related, applied holism. You accept everything. If you remember these will help you to keep your life creative. So here's the 5 elements. Stupa. Stupa is Hindu, right? Earth. What this? This one is fire, right? This wind, earth. Then, I forgot. Let me see. Yeah, earth, water, fire, and wind. 4 elements. At the top, we have a cosmos or universe. So, but the important part, mathematically, see these 2 figures. This is a dodecahedron, and this one here is a icosahedron. They are dual shapes. So we are all descendants of mitochondrial Eve, and there was a small group of around 20,000 people, 143,000 years ago. Oh, these our contemporaries, our ancestors, all disappeared. So we must be careful not to extinguish. The Earth is actually doomed because sun will engulf Earth eventually, but it will take a long, long time. Don't worry about this. So before that, we are not supposed to destroy Earth. And we are living in a very thin of air, which is called troposphere. It's up to 7 to 18 kilometers only. So 90% of climate changes are occurring in the troposphere. Above that, there's a stratosphere and mesosphere, and so on. So everything is circulating here under value. Actually, this is a joke. The proper name is Andrew Weil, spontaneous eating. And all these depend on holistic medication. And here, my main aim is nowadays is studying Ayurvedic medicine and ancient Chinese medicine. So this is an example of butterfly effect is an example of chaos. I'll not tell you more details. And also entropy. everything is just changing, changing of energy. And entropy is the word, coined word from N means energy, and trop means, this is a Greek word meaning transformation. But so everything has a cumulative effect. A little bit is okay, but if you keep taking trans fatty acid, you may have a problem. So I have written one paper, chemo approaches to life. So there are toxins. Now we have one more toxin. This is radiation. These cesium and strontium are very common. They have a half-life of 30 years. But they never talk about plutonium because half-life is this much. And also trans fatty acid. Cis is okay. Cis fatty acid is the ingredient which make up our membranes, cell membranes. But the problem is that here's the similarity. Strontium is very similar to calcium, so it can be absorbed in bone, like calcium, potassium. What we have to avoid is active oxygens. So these are strengths. This is ordinary, superoxide. Then this one is very dangerous. This is hydroxyl radical. This is 100 times stronger than this. This is used, you see, this hydroxyl radical is used as a radiation therapy of cancers. So if you get this, you can imagine how harmful it is. Okay, so today we are going to concentrate on these subjects: mathematics, music, and art. This is my life work, Lebensstunde, meaning life of longevity. So genuine musicians in their subconsciousness must sense the touch of the guiding of mathematical structure. This is our motivation, harmonic structure. Otherwise, how they can compose such music? In the same way, in the case of artists, how they can produce such art. Okay, so this one I just. There are many disciplines which are described by three elements. Number two, you know, Brahma, Vishnu, Shiva, right? And this quest to the west, Hanuman, Vishnu, Saraswati, no see. And this one is a Japanese swordsman, two-sword swordsman. Catch the rhythm, measure the distance, change the methods. These are the three elements of agriculture. So this is what we are concerned. Rhythm, melody, harmony. These are three elements of music. And today we are we are interested in the harmony. In Germany, there are three Bs: Bach, Beethoven, this is Bach. Bach, Beethoven, Brahms. So this is Bach. And Goethe once said, geometry is frozen music. But geometry can be replaced by mathematics, because in Middle Age Europe, there was 7 major subjects, and 3 subjects, grammar, logic, and rhetoric, used to be called trivium. Three, right? This is the origin of the word trivial. Remaining ones are arithmetic, geometry, astronomy, and music. Therefore, geometry means for middle-aged people, or for Goethe, geometry meant mathematics. There are some others. Music is a hidden arithmetic exercise of a soul, which doesn't know that it is counting. This is unconsciously they are doing. This is okay. These are the fundamental references. So we have to take this for granted. Do, re, mi, fa, sol, la, si, do, right? And C, D, E, F, G, A. A is important. This is La, right? Because they tune by this, starting from this. And Mi, Fa is a semitone. And Si, Do is also semitone. Please note that in one octave, there are 12 semitones. This is important. So, okay, so here, this is middle C, right? This is high C. But they use the same symbol. Why, musicians? Because they ignore, here we omit the difference, right? Multiple of power of 2 sound the same, similar, right? So another thing is that, for instance, So and Fa, right? We may think the difference between these two notes may be like this, right? But musicians count this by division. So this reminds us of logarithm. So this is the right answer. 9/8 is the difference, length of the interval. And we have found that this may be explained by Weber-Fechner law, that we humans sense the intensity of stimuli logarithmically. So the musicians must have known this. So interval 1, 2 is mapped on 0. And 0 means unison, the same sound. So now I come to the Pythagorean scale. Maybe I should show you first. Here. Oops. So this is 1 and this is 2. And in the middle we have 2/3, right? And then we multiply this by 3/2. But this one, right? But this is beyond the boundary too. So we multiply by 1/2, which gives Re, CD, right? Re, Do, Re. The third is this one, and this should be thought of as 27/16. This is La. This is the most important one. And please remember that the frequency of La is now tuned to be 440 hertz in modern concert. In the same way, we go this way. Up here, then a problem occurs. When you go back, then already, this one is very, very clumsy, right? This is actually against the rule of the law of Pythagorean law of small numbers. This is against the rule. So instead, we come back from 2 by this. And this one looks very simple, right? 3/2 to the power n. This is the integral part, right? Fuller function. But this is very important in mathematics, in connection with wearing numbers, wearing problem. So mathematically, these are just distance function. And you consider Q plus modulo powers of 2. So this one already I mentioned. So now I come to the arithmetic of with Pythagoras, you associate, naturally you associate this thing, like 3, 4, 5, right? 3 square plus 4 square equal to 5 square. And these 3 numbers were considered as holy in ancient Egypt. Osiris, Isis, and Horus. Those right-angled triangles with integer size are called Pythagorean triangle. And 3, 4, 5 is the first one. So here you know that you may know that the law of large numbers, statistics. This simply means that if you get many samples, then expected value will be close to the expectation, computable expectation. But here we have a Pythagorean law of small numbers. To get good harmony and consonance, there must be multiples of these numbers. I mean, if you fix one frequency, then others should be multiples by these. And finally, we'll come to this Coxeter's cyclotic numbers. So this one theorem. For this comes from Pythagorean scale. To lie within this, you have to have this P must be this. Like even in such a case, you can prove a theorem. Okay, this one, 3 seconds, right? This one is so, and then, okay, anyway. This one I should skip. Okay. The important part is that, as I mentioned, one octave has 12 semitones. So let's raise this 3/2 to the power 12. Then this is 129.7 so. But you see, 2 to the 7 is 120. This is remarkable. How Pythagoras was able to find such a number? There's other trials, like Giuseppe Verdi invented this. As you remember, nowadays concert pitches lies 440 hertz, but Verdi just set it 432, because if you go back, then the middle C would be 2 to the power 6, maybe. So this is Verdi pitch. This is a little bit different, right? No, this is okay. So this goes up here, 432, right? This is Verdi. This is just a simple overlapping of two signs. So if you have two waves and if you have some, this may be a problem because this fluctuates, right, this way, if they are not the same. And this creates beat and damage the harmonics. Oh, this one is more mathematical. How we, in order to remove the beat, you must make some arrangement. By this, you can get just the intonation. So you have 5 here, right? This one the same, but this one, we have 5 instead of that. But modulation is a problem. Modulation means you move to another key, right? So here, now modern music, they use just 1/12. But here we have 2 to the 1/12. And this is called equal temperament. So this is nearly, right? This is nearly 1.5, 3/2, but not exactly, but they are very near. So this is what is used. And La is almost 440. Now I come to aesthetics. So this one from an Hermits Miscellany by Yoshida, a Japanese hermit. But if you know mathematics, this should be named an hermit, right? Like Hermitian. In English, they say Hermitian, but in French, hermite, right? Another one is from the Zauberberg, is Magic Mountain by Thomas Mann. So the hero main character describes, sorry, crystals known as this too regular, so symmetric, with such perfection smells of death. So because we are analog creatures, which we should allow, as Da Vinci said, we should allow imperfection and a little bit anti-symmetry. Okay, so this is a very famous picture by Da Vinci. It's called Virtuvian Man. Virtuvius was an architect, but here you see how to compose. And this one, pentagon, right? One, and this one is 5 or tau sometimes. This is 1.618 and so on. More precisely, 1 plus square root of 5 divided by 2. So here I have a overstructure axiom. So I claim that pentagons are fundamental forms, and golden ratio appears as a ratio of this one. And then we have aesthetic theorem. First you draw the main parts and then inscribed in pentagons. Then detailed parts, right? So when you check the art like Hokusai, right? Then you may find any number, any ratio. But more or less, the main figure is speculated as a pentagon. Like if you want to draw the head of Hermes, right? It's easy to use this Hermes mask. And in Michel's talk, there appeared also the silver ratio. It's 1 to square root of 2, or sometimes 1 to 1 plus square root. And it is interesting to note that silver ratio appears in the basement of structures like Pantheon. But Pantheon or Horyuji temple have a ratio, golden ratio in solid state. So this is Hokusai's. These are you can find the ratios. This is Kepler's cosmological model. And Fibonacci sequence, just a minute. Somewhere I should have. So you see this, right? This is Fibonacci music, kind of, Fibonacci scale. Okay, then okay, let's go on. So final part is the law of cyclotomic numbers. And this was an experiment made by a very famous physicist, Helmholtz. And Joachim was a very well-known violinist. Joachim played and Helmholtz just observed. And they found these numbers, right? And I call this Helmholtz-Joachim scale. And funny thing is that, for instance, suppose you want to find between this, right? 6/5, 4/3. Then this is what you do, right? Actually, in school you cannot do this, but in Fourier series you can do this, and 3/2. So these are Fourier sequences. Looks very simple, right? But this is rather deep, and the Riemann hypothesis, in one way, is equivalent to the distribution of these simple numbers. And there are some, of course, some consistencies. Recall just the intonation. This is 5/3, 440 hertz. So finally, the Coxeter's law of cyclotomic numbers, right? You want to divide a circle into parts, right? 3, 4, 5. And actually 3, 5, these are Fibonacci numbers, right? 3 plus 5, 8. This is also Fibonacci numbers. So 3, 5, 8, these are in conformity with the small numbers. And the Fibonacci numbers, we used only 3, 4, 3, 5, 8. But if we suppose we use 13, then it will damage the harmony. So now you learned cyclotomic numbers. The law of cyclotomic numbers are somehow consistent with Pythagorean's law of small numbers. So here we have 3, 5, 3, 4, 3, 5, 8. These are 13 is not good. 3, 5, 8. These are elements of Fibonacci sequence, right? And regular polygons. These are compositions by ruler and compass. So how about 15 and 15? Actually, this is 15. 15 degree exists in Matthew Passion. Let me. So this is final. Here it's 15. I just play it again, then we'll finish. This is degree 15. Okay, this is all. Namaste. Thank you very much. Hey, Professor, I'm finished. Hi, hello?
Yeah, so thank you, Professor Kanemitsu, for this interesting talk. And you have given a real picture of mathematics and its scope, and it also reflects a mathematician's imagination. Of course, this was the aim of this lecture series, and I'm really thankful to you, Professor Kanemitsu, for having accepted our invitation and delivering this very informative session, and giving an exposure of some application of mathematics to especially to some young students who can see what how much what is the reach of mathematics, and especially you have touched upon some application of certain things in music. So thank you very much. And this was the last lecture of our popular mathematics lecture series. And I'm thankful to everyone for attending all lectures And in this series, I'm happy to inform everyone that there was a very good response from everyone. I had more than 1100 registrations, and these registrations were from 11 or 12 countries. So there was a good response. People showed a lot of interest in this in these lectures, and I'm thankful for your support, and it was very encouraging for me. And especially, I must make a mention that these sessions were not only attended by general public, students, professors, and but very senior mathematicians also. Even today, I see Professor Michelle Waldsmith is attending this lecture, and I'm really thankful to you, Professor Michelle, that you are present here. And really, it's a matter of matter of great encouragement for me, and with the presence of such great mathematicians in these lectures, I really felt blessed throughout. So thank you very much, everyone. And thank you, Professor Kanemitsu. And I hope that since I think we haven't met from the last 3 years, uh, I hope that we will be meeting somewhere in the near future. And I wish everyone a very good health, and please take care of yourself, and stay safe. So thank you very much. Thank you, one and all.
Thank you very much. Thank you.